There we go. Good morning, good afternoon, and good evening, everyone, and welcome back to the Point Distributions webinar. Today we have Adrian Ebert from Recam Linz talking about the construction of polynomial lattice rules by smoothness independent, component by component, digit by digit constructions. As a quick reminder, after the talk, there will be time for socialization, so feel free to stay on after we do questions after the talk. Adrian?
Okay, so thanks, and hello everybody who's attending this talk. First of all, I would like to thank the organizers for giving me the opportunity to speak in this webinar, and also for the technical support prior to this presentation. So I will talk today about the construction of polynomial lattice rules by smoothness independent component by component, digit by digit constructions. I will try to make clear what the title really means in the introduction of my talk. The presented results are basically joint research with my previous PhD supervisor, Dirk Nuyens, and also with my colleagues Peter Kritzer and Onikachi Oziziogu here in Linz, and also with Tetjana Stepaniuk. Yeah. So the agenda of my talk is as follows. I will start by introducing what lattice rules are, and I will also mention what the function space setting in the first half of the talk will be. Then I introduce a quality measure on which our algorithm is based. After that, I formulate the algorithm, the so-called component-wise digit-by-digit algorithm. I will show some theoretical results, but then also give some details about the fast implementation of the algorithm and present some numerical results. In the second half of the talk, I will try to show that, or try to move away from the special family of lattice rules and show that very similar arguments hold also for the QMC family of polynomial lattice rules. So, like I said, I start with lattice rules. Here below you already have a first impression of how a lattice point set looks. In particular, that's a rank 1 lattice. And so the main setting that we consider is the problem of multivariate numerical integration. And there we usually want to approximate the integral of an S-variate function f that maps from the S-dimensional unit cube into the real numbers. The corresponding integral we denote for short by I of f. And we want to approximate this integral by a quasi-Monte Carlo or short QMC rule. This will be denoted by Qn, so n will be the number of quadrature points that rule uses, and it depends on the particular integrand function f, and then on this point set of the xk here, where k runs from 0 up to n minus 1. And basically, this quasi-Monte Carlo rule is a weighted average, equal weights here, of function evaluations of our integrand function in the quadrature nodes xk. And what is specific for quasi-Monte Carlo rules is that the nodes, the quadrature nodes, are chosen deterministically, in contrast to Monte Carlo methods where the points are chosen uniformly at random usually. And now, if we consider such a quasi-Monte Carlo rule, then we are in need of a measure in which we assess how well we are doing in terms of the approximation problem. And this measure will in this talk be the so-called worst case error. So in particular, we define it as follows. So we restrict our integrand function of interest to a particular function space f here, that will be a normed space, in particular Banach space, and we have a QMC rule Qn with underlying points at Pn, and under these assumptions, the worst case error of Qn with respect to the function space f is defined by this expression below here. And this expression is basically the absolute value of the integration error of a function f, and there we take the supremum over all functions f that lie in the S-dimension. So this is, like I said, the worst case error. We denote it by E sub n comma s, and it's in particular depending on the function space, but not on a particular integer function itself. Yeah. And one particular family of QMC rules are so-called lattice rules. In particular, we will focus here on so-called rank 1 lattice rules. A rank 1 lattice rule is a quasi-Monte Carlo rule with quadrature nodes at Pn that has this special form here. Let me try to explain you this. So basically, we have a integer vector z of length s that we call the generating vector of the lattice rule. And then we basically take the scalar product of the number k with z, then do modulo n and divide by n. And here k runs from 0 up to n minus 1. And this is basically the point set of the lattice rule. Two examples are you can find here below of such lattice rules. To make it a bit more evident how the points are actually generated or constructed, let me give you the following example. So, like before, the node set of a lattice rule Pn is defined in this form. And if we move to a particular example of n being 32 points and our generating vector being 1,9, we can generate the points as follows. So the first point corresponding to k equals 0 is simply the point 0, 0 according to this definition. The next point would then be the point z over n. So it's 1 over 32, 9 over 32. And then for k equal 2, we get this point, and so on. And basically, we add this, this orange vector here to the previous point to obtain the next point. At some moment, though, what will happen is that we will actually move outside this unit box if we just follow this scalar product k times z. But then this fractional part, or this taking of the modulo here, will lead to the fact that our point is mapped back inside our unit box here, or in general, the unit cube. And in this way, we always stay in our box. And if we continue to add points in this fashion, we see that the points fill out the space quite well in this example. And that in the end, we end up with our 32 points that the lattice point set has here. It is not so clear, though, that we will always get such a nice distribution. In general, the generating vector z of a lattice rule influences the quality of the points, and in particular of the approximation for the integration problem quite a bit. So we can be lucky, we can have well-distributed lattice. In this example here, we have 89 points and a generating vector 1,34, and then we get such a nicely distributed lattice. But we can also be slightly unlucky, namely by choosing such a generating vector, 1,43, with the same number of points, and that would result in such a lattice node set. And you can see here that while we still have this kind of lattice structure, the gaps between separate pairs of points are quite big in this example, opposed to the example on the left. And therefore, we just formulate this partial goal that we actually are interested in generating vectors such that the obtained rank 1 lattice rule Qn is well suited for numerical integration. And we will later see that this is yeah, directly linked to the worst case error being small.
Adrian, can I ask a quick question?
Yeah.
So when you're saying well distributed here, is there a certain technical definition, or are you just referring to like, general visual of them being well
Yeah.
distributed?
Well, I mean, if you have like notions of discrepancy in mind, you can already see that this will probably give a lower discrepancy
Hmm.
than this. But in this example, I don't really have something in mind. One
Okay.
can show that for certain examples, like this worst case error that I introduced, is actually directly related to certain discrepancy notions. But here I just meant it like without going too much into technical definitions.
Okay, thank you.
Yeah. Um, Okay, so what is still open to kind of set or to choose is the function space that we consider, which already appeared in the definition of the worst case error. It is quite commonly known that lattice rules work in particularly quite well with periodic functions. And that's why we will consider those classes of functions here. So in particular, we consider one periodic continuous functions f that can be represented in terms of an absolutely convergent Fourier series in this way here. So f of x is given by this Fourier series where the Fourier coefficients f hat of h are defined like this. Um, yeah, and for such functions, one can, by quite trivial arguments, immediately show that the integration error of the QM0 Qn with generating vector z um, is expressible by this term here on the right-hand side. And that's basically um, a sum of Fourier coefficients. And I have to explain this function delta n is basically defined like here, and it means that if the argument is equivalent to 0 modulo n, then the function is 1, and otherwise it's 0. And in this fashion, this here is the sum of all coefficients f hat of h, where h belongs to this set. And this set is usually called the dual lattice. Yeah. Um, right. Um, now, having observed this, and we'll come later back to this previous identity, in order to define a proper function space, it is for periodic functions quite common to base the definition on the decay of the Fourier coefficients f hat h of the function. And if they're decaying sufficiently fast, then we say they're in the function space, and if not, then not. And for this purpose, we usually measure this decay of the coefficients by a decay function, which we will call R alpha of h here. For the univariate case, this is basically given by this expression. So it's 1 if h is equal to 0, and otherwise it's the absolute value of h to the power of alpha. And you can already see here that if the absolute value of h increases, then also our alpha of h increases. The multivariate generalization is given in this product form. And what one should note is that the smoothness parameter alpha, so it's called the smoothness parameter, um, is bigger than 1 and basically determines how fast later the coefficients are supposed to decay. There's another thing which I have to add here, which is quite common nowadays in quasi-Monte Carlo integration. So in order to overcome the curse of dimensionality, and that means in order to overcome the fact that we need a number of quadrature points that is exponentially depending on the dimension s, we introduce so-called weights. So it's weights are basically given like this. So it's a sequence of called gamma of real numbers, gamma u, where u are basically all the subsets from in the set 1 to s. And these weights or these real numbers for each u are supposed to measure the importance of certain groups of variables xu, where xu are all the xj with j and u. So just roughly speaking, the idea is that for a particular function, certain variables are more important than others and have a different influence to the function value. And by incorporating these weights in the definition of the function space, one tries to model this importance structure for certain classes of functions. And this is then, in a sense, incorporated in the definition of now this weighted decay function, R alpha comma gamma, where we have, in a sense, the previous definition, but now we add the inverse of this weight gamma of sub h, where sub of h is the support of our vector h. Yeah. And based on this decay function, we can, I forgot to say that actually the definition of this decay function, which might seem a bit arbitrary, is not so arbitrary because one can actually show that this decay function is directly related to the existence of certain mixed partial derivatives of the integrand function. Yeah. And so based on this decay function, one can now finally define our function space. So we will define this Banach space E S comma gamma alpha by the following norm. So it's basically a supremum norm over all indices, and then we have the product of the absolute value of the Fourier coefficient f hat of A.
I believe Adrian is frozen. Is he? Okay, so it's not just me.
Do you want to pause the recording?
Yeah, I'm gonna pause.
Okay, so can see it?
Yes.
Okay, then I continue. So I was basically saying that we can then define our Banach space E S gamma alpha by this norm here. And this norm, you can just basically understand it as a supremum norm of the product of absolute value of f hat of h times this decay function. And it basically means since the decay function increases as the norm of h increases, that in order to make the norm still finite, our coefficients need to decay sufficiently fast. Yeah, so that is the idea of the definition of this norm and the decay function. And you can already see that that the smoothness parameter here determines how smooth the function is. So it does not only determine the decay of the Fourier coefficients, but also, in a sense, the smoothness of the function. Okay. Yeah, and then coming back to the previous identity that we had for the integration error, one can now use this expression and apply Hölder's inequality to get such a bound here. So it's basically bounding the absolute value of the integration error by two factors. The left factor we can see is immediately the norm that we defined, and the right factor will turn out to be the worst case error of our lattice rule with respect to the introduced space. And just make this clear in this theorem here. So basically, our worst case error of the lattice rule of generating vector z is exactly of this form here. And this form will, in a sense, reappear when we introduce the alternative quality measure in the previous slides. So takeaway message at the moment is just that we could relate the integration error to the worst case error, and the worst case error can be expressed in this more concrete form here. Okay, because now we will introduce a slightly different measure, namely we will call that T alpha of n comma z. And this measure is basically as before, so it's the same expression, but now we are not allowing indices in the whole the whole integer vectors of length s, but we have like a truncated index set mn comma s, which is basically the truncated box with side lengths n minus n minus 1 to n minus 1. You can see here for an example lattice like this on the left-hand side, our set of indices in the set MNS with the additional condition that the indices lie in the dual lattice would look like this. And basically, the number of or the coefficients that lie in that set then depend or then determine how large the value of the quality measure is. Yeah, and so this quality measure can be immediately related to the previous worst case error for our function space. So that's what this lemma says. So under some technical assumption on the components of our generating vector, we can show that the difference between worst case error and alternative quality measure is bounded by this in this fashion here. And this is basically a factor of 1 over n to the alpha, which is the desired rate in our function space, and then some expression that depends on the weights gamma u. And now we can use this to observe the following. So if we just plug in the definition of a worst case error, which is this, then we subtract and add our alternative quality measure T alpha, and then we can use our lemma to bound the first difference here by the same expression, and are just left with the second. The second summand here in the bound we can estimate further by Jensen's inequality to obtain this expression. And this is basically, we reduce the alpha to be 1 and we reduce the gamma to be gamma of 1 over alpha and raised it to the power of alpha. For alpha bigger than 1, this estimate holds. And basically what we gained, the insight that we gained is that if we can find generating vectors such that the part in the braces is small, then also our worst case error will be sufficiently small. So that makes it kind of valid to use this as a alternative quality measure. I formally introduce now again this measure T for the limiting case of alpha equal 1 as this expression. And then I give you the following definition. So this definition is originating from an article or from articles by Koroboth, and it's a definition of optimal coefficients modulo n. It basically says in our setting that the components of our generating vector are called optimal coefficients modulo n if for any delta bigger than 0, our quality measure satisfies this bound. And this is basically a bound that says we want our t to decay roughly of order n to the minus 1 plus arbitrarily small delta. And the involved constant should also be independent of s and n. Yeah. Okay, so having introduced these alternative quality measures, we will try to introduce an algorithm which is supposed to find us such good generating vectors. So what one can immediately see is that if we would carry out an exhaustive search over all possible generating vectors z lying in the set from 0 up to n minus 1 to the power of s, then this would be infeasible, since this search space has cardinality of order n to the power of s, and is therefore depending exponentially on the dimension s. But to still find good generating vectors, in QMC literature, there were some other algorithms proposed by Korbov and then later also Sloan and Restorff, namely so-called component by component, or short CBC constructions. And these are basically greedy algorithms that really select the component of the generating vector, one component at a time, and still achieve good results regarding the worst case error behavior. Such constructions are nowadays also quite fast. So the state-of-the-art construction algorithms have a complexity of OS n log n. So to construct a lattice rule in s dimensions with n points, we need OS n log n operations to construct the generating vector. And here I will explore a different algorithm which goes back to this article by Korbov, in which we extended to the modern weighted QMC setting. So the first idea that I will only briefly mention here is that the quality function, yet another quality function that our algorithm uses, is related to this identity here. So what can be observed is that this function here has a Fourier series that looks like this. And especially this expression here is closely related to our function t, or our quality measure t that we introduced. And I won't give you all the details here, but this is basically the way how we came up with the quality function for our component-wise digit by digit algorithm. So this might look quite complicated. This is the definition of our function. If you're interested into details, I will give you the references to our articles later. But for the moment, I just give the definition here. And what is important to remember is maybe that this function here, small h, depends on r, which is a counter for the dimension, and v, which is a counter for the digits and the weights. And it has one argument, and can then be evaluated in this fashion. And based on this, we basically can define our algorithm. So I try to explain you how the algorithm works. So we have as an input an integer n, the dimension s, and the weight sequence gamma. Then we set the first component of our generating vector to 1, and additionally we set the the digits of the remaining components of our generating vector to 1. And then what we do is we have two loops. We have one loop over the dimension, that's the CBC part, and we have one loop over the digits, that's the DBD part. And then inside these two loops, we basically choose the digits of the particular components one by one. And that is done by minimizing over the bits. So it's two choices, 0 and 1, of this function here. So it's the previous part of the component plus, and then it's either 0 or 1. So it's either we add the bit or we don't add it. And whichever minimizes our function h, small h, will be chosen as the next bits. And then we update this expression accordingly. And then in the end, we basically obtain all the components of our generating vector by setting the respective component Vr to be Vr, n. And then we obtain a generating vector for a lattice rule with n equal to 2 to the n points in s dimensions. just trying to make the procedure of the algorithm clear. So like I said, the generating vector Z is constructed component by component, and each component is built up digit by digit. So after the first, component is just set to be 1, and then we basically set the first bit 1 of the next component, do this optimization to set all bits of the particular component, and then move on to the next, and so on. I will try to give I will give an explicit way of how the construction cost can be reduced and computed. But what is noteworthy here is just that, just based on the definition of the algorithm, one can already see that the construction is extensible in the dimension S, which is a favorable property for such construction algorithms. Yeah. We then obtained some good theoretical results regarding the error convergence behavior of generating vectors constructed by this algorithm. So basically the statement of the theorem is the following. So under some given parameters, if we run the algorithm with the parameters to obtain a generating vector, then the quality measure T of this generating vector satisfies this, say, rather technical bound. Additionally, then, and I forgot to mention, in this case, we make a slight restriction. So we don't allow these very general weights, but in our case, these weights, gamma U, are actually product weights. And product weights mean that they're basically the product over all J in the subset U, gamma J, and the gamma J are just reals. So, yeah. So the weight sequence gamma is given by a sequence of gamma J. And now the additional statement is, if the weight satisfies this summability condition here, then the bound is actually independent of the dimension S, and we get also that the components of the generating vector are optimal coefficients modulo n. Yeah, and with the connection to the worst case error that I already tried to make evident earlier, we can also get immediately a result for the worst case error, namely that under the same assumptions, again using this summability condition, that then for any delta bigger than 0 and each alpha bigger than 1, the worst case error, this one here with gamma to the alpha, satisfies this bound. And again, the constant C is independent of the dimension and the number of points n. Yeah, that's in a sense the best result we can hope for, because we obtain basically the optimal convergence rate of the worst case error in the considered space. And one detail that I should mention is that if you look back to the definition of our quality function, you see that this quality function h does not depend on the smoothness parameter alpha in any way. And also in the algorithm, it does not appear as an input parameter. And now what we obtain though as a result is that even though we run the algorithm independent of alpha, we still get estimates and bounds for all alpha in this fashion here. And this is in contrast to state-of-the-art CBC algorithms, where usually one has an error criterion which depends on the alpha and which inputs the algorithm, and then one only gets a statement for this particular alpha. While here, the construction is independent of the smoothness alpha, and we get results for, in a sense, all alpha bigger than 1. So that's the smoothness independent part of the title. Yeah. Okay, regarding the fast implementation of the algorithm, I am going to skip the first part and move already to the fast implementation. So for the fast implementation, we can observe that the cost of the algorithm is mainly determined in just how costly the evaluation of our quality function small h is. So for the case of product weights, small h equals this expression, and we are aiming to evaluate this efficiently. So what we do is basically we define this term q here, which so basically what we do is we define this term q, which is this factor here, and save it. So this way we avoid to having to compute this for each m and yeah, for each r as well. Yes, and in this way we can then rewrite our quality function. In this way, we don't have to compute this anymore, just once in the beginning, and we can then use this recurrence relation to update this q for going from r-1 to r. And in this way, we can reduce the cost of a single evaluation of h to require only this many operations. And in this way, one inner loop over only the bits will be of cost n log n. And therefore, the whole algorithm can be, for product weights, executed is in Sn log n operations requiring O(n) memory. And so this is a good result because it's competitive with the state-of-the-art CBC constructions. One important thing to notice here is that usually these CBC constructions get fast because they use fast Fourier transformations to do certain operations. But our algorithm actually achieves the same complexity asymptotically, but without the use of such techniques. And therefore, it is also easier to implement. Yeah, so now some numerical results that I want to show. First, regarding the error convergence behavior. So for the error convergence behavior, the experiments that I did are as follows. So I considered basically generating vectors and the corresponding worst case error for lattice rules or generating vectors constructed by our algorithm and as a benchmark by the fast CBC algorithm. And then I basically did it for a fixed dimension of 100 for different weight sequences and for different smoothness parameters alpha. And this results in the following. So what you can see here is, so how you have to read this is the circles always correspond to results of our CBC DVD algorithm. The triangles correspond to the benchmark standard fast CBC algorithm. And then we have the color corresponding to our alphas. So blue would be alpha equal 2, green alpha equals 3, and purple alpha equal 4. And what one can see is that in general, the error convergence behavior for both construction is asymptotically the same, depending on the weight sequence, gamma j. It depends a bit how fast the decay is and also how close one is, or how big the difference between both convergence rates is. But in general, both algorithms give good results. One thing that one has to notice is that our algorithm uses like one run, since it's independent of alpha, to construct a generating vector, which then gives good error results for all considered alpha here. While the CBC construction needs to compute 3 different generating vectors that are then used for each particular alpha. So in a sense, we can save some work because our result is valid for all considered alpha. Regarding the computation times, so I just put a table here of computation times. So in bold is our CBC DVD algorithm, and then as a comparison, the fast CBC algorithm. In general, like I said, they're both having a complexity of Sn log n. That can also be observed in this table. We see roughly that our algorithm is by a factor of 2 slower That might be because the fast CBC algorithm, like I said, uses fast Fourier transformations, and these are usually done by compiled libraries or in C, while our algorithm was basically a MATLAB and Python implementation. And maybe by converting to a compiled library, we could still speed up our algorithm. Yeah, and so in the last part of the talk, I want to move to polynomial lattice rules. So basically, the whole procedure will be very similar to what we have done for lattice rules. So opposed to lattice rules, we consider now a different function space setting. So instead of having a Fourier series, we consider a so-called Walsh series. It is essentially the same, just that we have now Walsh coefficients f hat of k, and our basis functions are now Walsh functions. The Walsh functions are defined as this. I hope this is more or less known. I'll try to give a short illustration of such functions later. And like before, we will again introduce such a decay function now for our Walsh coefficients. This is also very similar, instead that we have now b to the alpha of floor of log b of k, but this is asymptotically still behaving like k to the alpha. Yeah. And based on this, we can again define our function space. Now, this is our function space WS gamma alpha, which is a weighted Walsh space. And opposed to these smooth functions that we saw before, if you now consider a very similar Walsh series, then you can see that these are basically step functions. So, yeah, and you can also see that here the parameter alpha or here beta, which before was in a sense a measure of smoothness, is now not so evidently related to the smoothness because, well, they are always step functions. One can see if the beta increases, then these steps here seem to get smaller, but it's not so immediately related to the smoothness as it was for Fourier spaces. Yeah, and then polynomial lattice rules are defined as follows. So polynomial lattice rules are called that way because the structure is very similar to lattice rules, but the difference is that instead of having an integer arithmetic, we are now having a polynomial arithmetic. In particular, we consider polynomials over finite fields, with b usually being the base and being a prime. And then what is crucial is this map Vm, which maps the formal Laurent series here to this expression, which is a number or real number in the unit interval 0, 1, the half open interval 0, 1. And basically what this map is doing is from this expression cutting off after m terms and in a sense inserting for the x the b to obtain then a real number. And what I should also mention is there's like a relation between integers and polynomials, namely that if we have such an integer n with base b expansion of this form, then we will often associate n with the polynomial n of x given by this form. And having introduced this notation, we can then define what a polynomial lattice pointer is. So we fix our base b to be prime, and then choose this polynomial p, which is called a modulus polynomial, that is supposed to have a degree of m. And we also have a generating vector g. And this generating vector, okay, I think there's a small mistake here. This should actually be g being in the set fbx, but to the power of s. So it's again a generating vector whose components are polynomials in FDX. And then our polynomial lattice point set is defined by this fashion here. And here you can already see it looks very similar to lattice rule. Before we had k times z over n, and now we have n times g over p. Yeah, and n runs basically from all polynomials with degrees smaller than m. And in the end, we will obtain b to the m points. So we always have a prime power of points for polynomial lattice point sets. Yeah. Just to give you two examples. So on the left, you can see the point set of a polynomial lattice for, say, a generating vector which gives a, at least by the eye, well-distributed point set, while one can also be unlucky and have like big gaps for such a generating vector here on the right-hand side. Yeah. Also here, the integration error of a polynomial lattice rule can be represented in terms of the Walsh coefficients, and you can already see it's quite similar. So the further strategy to come up with a similar algorithm is almost identical. So we again introduce then similar quality measures now with our newly introduced decay function. We again can relate that to the worst case error expression in our Walsh space, and then in the same way define our quality function and formulate the algorithm. So again, quality function looks for product weights quite similar. Now you just have to remember that all the arguments are polynomials instead of integers. The algorithm looks then also almost identical, just again that we now don't build up in a sense the digits of a integer, but we now kind of determine the coefficients of the particular polynomial component. Yeah. Right, and this algorithm can therefore in the same way again be implemented in a very fast way. And usually what we do is we fix for our later numerical experiments the base b to be equal to 2 because it simplifies some computations. Yeah, and a very similar statement holds also with respect to the error convergence behavior. So again, under the summability condition, we obtain essentially the same bound for the worst case error in our Walsh space. And again, a fast construction is available of here cardinal of complexity Sn log n or Sm 2 to the m. Yeah, and also the numerical results look similar. So we basically repeat the same experiments for the new algorithm with then the worst case error for the weighted Walsh space, and we get very similar results. Again, the algorithm seems to be competitive with the state-of-the-art CBC algorithm. Yeah, and that is basically everything that I wanted to talk about. So thank you for your attention. I have some references here if you want to look at it. So these two articles are with my collaborators that I mentioned in the beginning. They're currently submitted, but are available on arXiv. Yeah.
Thank you very much.
Any questions for our speaker?
Yeah, I guess let me perhaps start. So Adrian,
Yeah.
do you hear me? So this algorithm where you look for generating vector C's, you start always with the vector 1, 1, 1. Is there perhaps a better way to start the algorithm?
You
Depending
mean
on your input parameters, perhaps the vector 1, 2, 3, 4, 5, I don't know, would be better suited. I guess, I don't
yes,
know.
so let me maybe quickly look back. You still see my screen, right?
Yes.
So yeah,
Yeah. You
essentially,
mean this part or this part?
exactly, yes. You start with this one, right? That's the first step, is just to put a vector 1, 1, 1, and then from there you start to
Well,
apply algorithm
yeah.
and find a better choice.
I mean, so the first component, this, to just set the first component completely to 1 and then start with 2, that doesn't matter because it can be shown that, well, this is basically just reducing the number of choices. Here, well, here it kind of matters because choosing this to be 1 basically means that all components, if we run it for base, since we have 2 to the n points, means that we always will get odd numbers. And this is kind of what we want, because we want to be the greatest common divisor of the component and 2 to the n to be 1. And as soon as we have an odd number, we kind of assure that. And that gives them some properties. I think in the beginning, that was one of the assumptions, that the greatest common divisor between the components and n should be 1. And that's why we kind of need it there. I mean, technically, one could maybe also fix others, but we thought, well, it makes more sense to just fix the first and then have freedom of choice over the others.
Okay. Thanks.
Adrian, so do you plan to, or maybe you're already doing this, do you plan to tabulate these the good Z vectors and maybe make them available? Or
yeah, it could be done. It depends, of course, I mean, the algorithm really doesn't take very long if you need it for moderate number of points. So we did it like 2 to the 20 and 100 dimensions. It really just takes a few seconds. If you do very heavy computations, one could save it and then can avoid some computations. But since you saw, there's always still the weight sequence in it. So what one could do is one could pre-compute it for large n and for, like, say, common weight sequences. That one could do indeed, yes. But so I didn't mention it, but so I have a repository where the constructions are available. So technically, one can just use the code, run it, and then save it for yourself if you have to do some computations.
See, thank you.
So just perhaps to be clear, your code gives you one generating vector that's essentially good enough. Have you tried to find all generating vectors that are good enough in some sense?
Well,
the geometric shape.
Yeah.
Oh,
so the reason why these greedy algorithms work quite well is basically because there are quite a lot of good ones actually. So it is, I mean, choosing all, I think you would find quite a lot that are sufficiently good.
Yeah.
How good you want to get depends a bit on maybe your problem, if you have a computation in mind.
But it's just in general. So if you have a toy example, for instance, and say in dimension 2 or 3, right, and just set an error bar, say, okay, find all the good vectors that are essentially in a certain domain, and just plot them, right? I'm just curious what the shape would look like, and if this would also tell you something about the problem, or if you could just have a connection, say, with the dimension, the problem, and the shape of your good vectors, so to say.
Okay. I was gone. I don't know if you noticed.
Well, we see your face now instead of your
but my internet disconnected again. So I don't know if you said anything still when I couldn't hear it.
Oh, so my question was essentially, if you have a toy example, and you perhaps have plotted some good vectors in a certain domain just to see the geometric shape that represents your toy example and the amount of good vectors.
Yeah, no, I didn't do that. So we mainly look at the worst case error, and then the distribution should be quite good. Especially,
yeah, but again, you have already mentioned there should be many good vectors, and depending on the error bar you set yourself, right? I wondered perhaps you can see something out of the good vectors, so to speak, for each error bar. Is there something like a shrinking?
Yeah. So I did some, well, just some histograms of just compute for small n and small dimensions. You can compute all and see how they look. But it depends also there pretty much on the weight sequence that we use, how the shape looks. But usually, like, well, yeah. Well, I don't really have some concrete results, but I looked a bit at it. Yeah.
I see. All right. Yeah, thanks.
Maybe you said this somewhere and I missed it, but the lattices that you were getting, did you check? Did you have results as to how that fares in regards to discrepancy? Like, do you get point sets that have seemingly optimal discrepancy or nice properties like that?
Yeah, no, I did not check that in specific. Yeah, one could have, well, optimal, I wouldn't say optimal because, yeah, again, it's like a greedy algorithm that just minimizes a related error notion. So if one would like think of going more in the field of point distribution theory and replacing, say, the worst case error by some discrepancy notion that is computable, possibly also weighted, then one could do that. But I did not compute it and check. But I think there are I think there should be certainly some connections to the worst case error expressions and these discrepancy notions. Yeah.
Other questions for our speaker?
Perhaps the last one for me. So I was just wondering, I mean, you used your Fourier series representation, even the Walsh representation, but are those really necessary? I mean, could you just use any eigenbasis or basis space for your function space and do the same calculations with it?
Well, I think that, I mean, technically it could work, but usually why one does that is to get good representations of the error. So if you just choose an arbitrary basis and say the same point sets, then it gets quite messy because your worst case error expression is then not so easily computable anymore.
Yes,
and that's why.
No, I'm not just meaning an arbitrary any basis, but perhaps some basis that might be easier for the problem at hand or stuff, right? I mean, you just could use essentially the basis that's best for your problem, and perhaps it will yield things that are more equitable.
So if you use something else than Fourier or Walsh basis, then it might be, so there might not be a quasi-Monte Carlo family that matches that one. Because usually lattice rules match Fourier basis, and then you get this identity for the integration error that I showed, and the Walsh is the same with digital nets or polynomial lattice rules. If you choose like, say, you know, the genre polynomials, or if you go to a Hermite space, then it is currently not possible to get like a, well, you can try to use them, but then the error analysis gets quite complicated. That's why one usually uses that. And what I maybe forgot to mention is that considering this Fourier basis, for example, is not much of a restriction because you consider them periodic functions, but you can relate these periodic function spaces to Sobolev spaces, and results from the Coburg space with the Fourier basis transfer to these Sobolev spaces. So yeah, So there are relations between certain spaces.
All right. Thank you. Thank you very much.
Any other questions? Just in case, I will now stop the recording.